the name of Almighty God, I'm Mahsa Sankoshi, and today I want to talk about the advanced evolution of massive stars, new reaction rates for carbon and oxygen nuclear reactions. Now, today I want to go through the introduction. Massive stars are keynotes of the chemical evolution of the universe, synthesizing heavy elements in their interior and enriching their surrounding through type 2 supernova explosions. The supernova ejecta composition reflects the cumulative effects of successive nuclear burning states and extensive nuclear synthesis during massive star evolution. A detailed understanding of stellar evolution phases from hydrogen to silicon burning and their role in driving nucleosynthesis remain incomplete, especially for the most advanced phases, for example, beyond the um, helium exhaustion. The specific density and temperature conditions reached in these phases enable a broad range of nuclear reactions to occur, including S-process and nucleosynthesis contributing to heavy element formation. These reactions also influence the stellar fate by determining the remnant type and mass as well as the composition of the supernova ejecta. Only the mass energetic reactions involving the most abundant elements significantly derive stellar evolution and impact the chemical structure. Among these, nuclear reactions involving carbon and oxygen are key to massive star evolution. Ongoing experimental and theoretical efforts aim to determine the rates of crucial reactions at the relatively low energy of the astrophysical interest, with improved accuracy and reliability. For reactions involving carbon and oxygen are of particular interest in the context of advanced evolution. First, the carbon 12 alpha and gamma oxygen 16 reaction, primarily active during the latter part of helium burning phase, governs the carbon 12 oxygen 16 ratio in stars and potentially affects the carbon monoxide core mass at the end of the helium burning phase. In particular, have shown that a lower reaction rates lead to a higher carbon-12 oxygen-16 ratio, with consequences on stellar evolution and structure, eventually influencing the explosiveness. The carbon-12 and oxygen-16 ratio is ultimately propagated throughout the universe when a massive star explodes, ejecting the carbon and oxygen from its outer layers, which they contribute to the formation of newer stars. Second, the fusion reaction, carbon-12 plus carbon-12. The most important reactions during this carbon burning phase impact both the nucleosynthesis and the final fate of stars. Third, the fusion reaction, oxygen 16 plus oxygen 16 is the main reaction during the oxygen burning phase. Finally, the fusion reaction, carbon 12 plus oxygen 16 is expected to occur at the transition between carbon and oxygen fusion. Mainly during shell burning, this reaction likely contributes to heavy elements production from the end of the core carbon burning phase to the core oxygen burning phase. Stellar evolution models rely on nuclear physics, which pose the choice of isotopes and adopted reaction networks, strongly influencing stellar evolution and nucleosynthesis. Nuclear reaction rates are obtained from experimental cross sections, measurements, and theoretical predictions, which are both subject to uncertainties. At the low energies typical of stellar interior, here's a few megaelectron volts. Nuclear reaction cross sections are extremely small, making precise and reliable rate measurements particularly challenging. Consequently, variations in these rates propagate into uncertainties in stellar model predictions. While widely used, nuclear rate compilation include newer rates are available, offering the potential to improve our modeling of stellar nuclear physics processes. The aim of this paper is to explore the newly available reactions rates with regard to their potential impact on the advanced stage of stellar evolution, nucleosynthesis, and the ultimate fate of massive stars, with a particular focus on chemical abundances and stellar structure. In the previous paper, examined the impact of updated nuclear reaction rates for carbon 12 plus carbon 12 during the core carbon burning phase. Here we extend this analysis by incorporating revised nuclear rates for the carbon 12 alpha gamma 6 oxygen 16 reaction. We also expand our investigation to include the oxygen burning phase, exploring the consequences of adopting new reaction rates based on the hindrance scenario or in theoretical nuclear model predictions for the carbon 12 plus oxygen 16 and oxygen 16 plus oxygen 16 reactions. The outline of this paper is as all follows. In the sections 2, we describe the input physics included in the Geneva Stellar Revolution Code, GENET. In section 3, we describe the nuclear rates that we are testing in our models. In section 4, we represent the impact on stellar evolution from carbon burning up until the oxygen burning. Section 5, section 5 presents the resulting heavy elements nucleosynthesis with particular emphasis on the effects on the S process. In the section 6, we assess the implications of our models for the final fate of massive stars. Finally, we discuss our results and conclude in section 7. Table 1 illustrates and describes reference for reactions important during carbon burning and oxygen burning phases. Now I want to go through the next sections, which is the stellar evolution code. We model the evolution of massive stars using the stellar evolution code GENEC as described in Eggenberger and his colleagues in 2008 and D24. We computed both rotating and non-rotating models at solar metallicity Z is equal to 0.014 for these different initial masses 15, 17, and 20 m. Each model was evolved from the zero age main sequence to oxygen exhaustion, defined as when the oxygen core abundance X oxygen 16 drops below 10 to the power of minus 3 unless otherwise stated. The latest version of the GENEC code was developed to better capture the advanced phases of massive star evolution. In this version, radiative opacities are generated within the OPAL opacity table from the Iglesias and Rogers in 1996 for temperatures lower than 1 gigakelvin. At higher temperatures, estimates from the Potonant in 2017 are used. The equation of states EOS combines a low temperature and density regime, which includes partial ionization effect with the fully ionized plasma equation of states of Chimers and CC in 2000. These two regimes are matched at the conditions logarithm temperature is greater than 7.55 and logarithm density is greater than 2.8 for a typical 25 m star. This corresponds to transition between the two equation of states in the core during the helium burning phase. We used the gray atmosphere approximation and treated convection according to the mixing length theory with alpha MLT is equal to 1.6 calibrated to the sun with the solar reference abundances from Aspelund and his colleagues in 2005. As in D24, we use the Schwarzschild criteria for convective stability and applied core overshooting for phases prior to carbon ignition with an overshoot parameter d over is equal to 0.1 HP, where HP is a pressure scale at scale height. In the present paper, we use the same formalism for rotation as described in 2D24 with V initiation divided by V critical is equal to zero point 0.4 and follow the cellular rotation hypothesis by Jean in 1992. For the sake of comparison with D24, we don't take into account the action of magnetic fields. However, magnetic torques are drivers of angular momentum transport in stellar evolution. The combined impact of the new rates and magnetic angular momentum transport will be the object of the future work. Now I want to go through the nuclear reaction network and rates. The nuclear network used in GENEC during the advanced evolutionary phases has been updated from the version employed into D24 to include the primary reactions that derive the energy generation and chemical evolution during carbon negative Na negative and oxygen burning. The current network, the GE Valnet 48, comprises 48 species. It builds on the spine network. GE Valnet 25 introduces in Gilifers and its colleagues in 2025 with the addition of secondary alpha chains to enable the tracking of reactions such as oxygen 16, oxygen 16p31. The full list of explicitly tracked isotopes is detailed in application A. Furthermore, we have updated reaction rates of 7 key nuclear reactions that significantly affect the most abundant elements and the neutron density following the recommendations of the NetGen database and is identified by Chaplin and his colleagues in 2018 for reactions not directly involved in our study. Rates were taken from the NASRI 2 database, Zhu and his colleagues in 2013, or from CF88 when NACRI 2 data were not available. The main focus of the present study is to explore the impact and sensitivity of the measure or theoretically predicted reaction rates are listed in tab 1 for key nuclear reactions involving carbon 12 and oxygen 16. These include the carbon 12 alpha gamma 6 oxygen 16 reaction, which plays a critical role during helium burning, as well as the carbon 12 plus carbon 12 plus oxygen 16, and oxygen 16 plus oxygen 16 fusion reaction that occur during the later stage of stellar evolution. Now I want to go through the carbon 12 alpha gamma 16 oxygen. One of the most important nuclear reactions during stellar evolutions is carbon 12 alpha gamma oxygen 16. This reaction primarily occurs during the helium burning phase in competition with the 3 alpha process and derives the carbon 12 oxygen 16 ratio at the end of this phase. In the present work, we adopt the update reaction rates from the De Boer and his colleagues in 2017 instead of those from Coons and his colleagues 2012, which were used into D24. The rates provided by the De Boer and his colleagues in 2017 are more accurate and have smaller uncertainties as illustrated in the figure 29. Figure 1 compares the two sets of rates and shows the predicted helium burning temperatures in both the core and the shell. In the region of interest, the De Boer and his colleagues in 2017 rates are systematically lower than those of Coons and his colleagues in 2002. This revision results in a slightly shorter helium burning lifetime by 2% and approximately 15% increase the carbon burning lifetime, shorten and the oxygen burning lifetimes according to internal report, and a higher carbon 12 oxygen 16 ratio at the end of helium burning along with the slightly hotter and the denser core according to the pattern and Zuchbol 2020 boosts carbon monoxide core mass and central carbon 12 mass fraction at the end of the helium bearing influence the final fate of massive non rotating stars. Variations in these parameters between models can thus affect the nature of the impact remnant produced at the end of the stellar evolution. This has been recently confirmed, for example, by Steen and his colleagues in 2025. She also references therein who examined the impact of the arbitrary positive negative 3 sigma variation and reaction rates based on the Kuhns and his colleagues in 2002 data and showed, using a different methodology than the one employed here, that such variations influence both the mass and type of remnant. In our models, we find that the carbon monoxide core mass at the end of the helium burning is largely insensitive to change in the carbon 12 alpha gamma 16 oxygen reaction rates. For instance, we obtain M carbon monoxide is almost equal to 2.35, 2.92 M and 4.10 M for our 15, 17, and 20 M models respectively. However, the carbon 12 oxygen 16 ratio is affected, increasing from the carbon 12 oxygen 16 is equal to 0.55 with the Kuhn and his colleagues in 2002 the rates to carbon 12 oxygen 16 0.65 with the updated rates from the Deboer and Scholars in 2017 and relative increase of about 20%. This is expected as the lower carbon 12 alpha gamma oxygen 16 rate leads to fewer alpha captures by carbon 12, resulting in more carbon 12 remaining and less oxygen 16 being synthesized. The small change observed in carbon monoxide core mass is also consistent with expectations, as this quantity is primarily determined by the convective core mass during helium burning, which in turn depends on the total energy released by nuclear reactions. Since the carbon 12 alpha gamma oxygen 16 reaction doesn't dominate the energy generation in this phase, the overall energy output remains nearly unchanged between the two models. We will further explore the implication for the final fate of these models in next sections. 3.2 fusion reactions, carbon 12 plus carbon 12 and carbon 12 plus oxygen 16 plus oxygen 16 in Monprix Band and his colleagues 2022. Hereafter M22 and D24, it was shown that recent measurements for the carbon 12 plus carbon 12 reaction exhibit significant deviations from the commonly used CF88 rates. These updated rates account for suppression trends or hindrance of the fusion cross-section at low energies and also incorporate as a resonance at 2.14 megaelectron-volt, first observed by Spilance and Scarlett in 2007 and later supported by SCLO measurements. Fruit and Scarlett in 2020, we previously demonstrated that the adoption of these new rates yields a shorter carbon burning lifetime, a hotter and denser burning core, and a shift in the transition from a convective carbon burning core to a radiative carbon burning core to higher initial masses, approximately 29 and 25 M for rotating and non-rotating models respectively, compared to about 27 and 25 M with the CF88 rates. Here we extend the analysis beyond core carbon burning to explore the impact of these updated rates on the carbon shell burning phase as well as on the core NE and core oxygen burning phases. In this later stage, the oxygen 16 and oxygen 16 fusion reaction becomes increasingly relevant, along with a potential contribution from the carbon 12 oxygen 16 reaction. Given their similarity to the carbon 12 plus carbon 12 reaction, we adopt a consistent modeling approach for all three reactions and compare the resulting outcomes. We focus mainly on three representative stellar models as described below. In the absence of experimental data within the relevant gamma windows for these reactions. This study also serves a preliminary sensitivity study aimed at guiding future experimental efforts as the first energetic reaction of interest for massive stars after helium burning. Carbon fusion takes place for temperatures of at least zero point 0.6 up to zero point 0.8 gigakelvin. You see that we have a carbon 12 plus carbon 12, which gives the magnesium 24, and in the difference three equations where Q or Q value refers to the energy released or consumed by the reaction. For this reaction in particular, substantial experimental efforts and advances in measurement techniques have enabled direct measurements to probe increasingly lower energies. However, the available data are still suffering from significant uncertainties. At the center of mass at energies below 2 megaelectron volts, Spilana and his colleagues 2007 to overcome the challenge posed by low energy measurements. Alternative indirect methods such as the so-called Torsion-Hurst method or THM have been developed. This technique provides the indirect estimates of the carbon 12 plus carbon 12 reaction cross section, which are several orders of magnitude higher than those obtained via direct measurements. While these data have been employed in stellar evolution studies, their interpretation is remains contentious within the community. Further work is needed to reconcile the results of these two complementary approaches. In the present paper, we focus exclusively on the impact of the new rates obtained from direct measurements and theoretical nuclear model predictions within the temperature range relevant for the core and shell carbon bearing phases at temperatures above 1 gigakelvin during both hydrostatic and explosive carbon minus carbon negative and oxygen bearing phases, with the carbon 12 plus carbon 12 fusion reaction becomes subdominant. The following reaction nuclear reaction becomes relevant. Suitable conditions for reactions to occur when the oxygen 16 abundance is highly enough, typically between core carbon exhaustion and the onset of oxygen burning, as well as in the shell carbon burning regions. Although these reactions has a lower probability to occur than the reactions 1 and 3, its main impact lies not in the energy production but in its potential to influence nuclear synthesis yields during the carbon negative and oxygen burning phases. Experimentally, this reaction has recently been revisited at low energies of astrophysical relevance, enriching the dataset as that has been available since the 70 decades. These new measurements provide models evidence for the existence of the resonances in the deep subcolumbar regime. The last major reaction for which we vary the rates is the dominant nuclear process during the oxygen burning phase, occurring in the at a temperature of about 1.9 gigakelvin. So you are watching the figure 1. Figure 1 illustrates reaction rates for the four main nuclear reactions involving carbon 12 and oxygen 16. Top left rates from the De Boer and his colleagues in 2017 normalized to Kunz and his colleagues in 2002. Reference for the carbon 12 alpha gamma oxygen 16 reaction. The gray hatched areas indicate the temperature range where core and shell helium burning occur in the GENIC rotating model explored mass range. For the rest of the panels, nuclear reaction rates are taken from the CF88 black HIL res blue and TDHF magneto, all normalized to the CF88 rates, which sigma nu is greater than NR and greater than CF88. Shaded areas with corresponding color coded indicates that the temperature range where core and shells carbon burning and core oxygen burning take place in the 15 and 17 genetic rotating models. Due to the experimental difficulties to measure this reaction accurately, mainly caused by the technical availability of the oxygen targets and a large number of exact channels, only scarce and sometimes disagreeing measurements from the 17th and 18th century are currently available in the Fernandez and his colleagues in 1978 and etc. Based on the available experimental data, several models with a small number of parameters have been developed to describe the astrophysical S factors and derive the corresponding nuclear reaction rates. The standard and most widely used reference is CF88, which was originally implemented in the genetic code and remains a common choice for stellar evolution modeling. For fusion reactions, in particular, phenomenological model deviating from the CF88 at very low energies, the hindrance or HIN model has recently been incorporated in GENEC. Both models are explored in this paper and their implementation is described in detail in section 2.2.1. Alternatively, modern theoretical approaches can provide insight into the behavior of the cross sections at a very low energies. These methods help constrain the rate trends or in the absence of experimental data offer predictive estimates that are used in a stellar evolution codes such as those available in the relic database. For the three fusion reactions that are discussed in the present work, reaction 1, reaction 2, and reaction 3, multiple frameworks have been used in the literature. The time-dependent Hardy-Fock method, hereafter the TDHF, and etc. And the microscopic alpha cluster model. However, these models are subject to limitations arising from the approximations and assumptions needed to perform the computations. For example, TDH and microscopic alpha cluster models are unable to capture resonance in the cross sections and may omit the relevant physical phenomena, especially for complex systems such as the carbon 12 plus carbon 12, a combination of direct measurements of nuclear reactions and model based constraints on the energy dependence of the reaction rates is therefore necessary to advance towards a more accurate descriptions of the nuclear reaction rates. The approach followed in this work is to compare the empirical data-driven models with the TDH model, which is described in the more detail in section 3.2.2. Now I want to go through the data-driven frameworks we use as reference rates for the three fusion reactions. The parameterized analytic formulated from the CF88 as standard reference widely used in the literature. In addition, we also employed rates from the phenomenological hindrance scenario. This scenario accounts for the suppression in the fusion cross-section at deep sub-barrier energies, a phenomenon observed in medium mass fusion systems, hereafter simply referred to as systems in a Q is less than zero systems. The hindrance effect is clearly observed as a more rapid decline of the cross sections than expected, suggesting the existence of a maximum in the S factor whether or not a similar suppression occurs in Q is greater than zero system is still unclear. Although this trend has been experimentally investigated across a wide range of systems, it remains under debate whether such suppression also affects right fusion system relevant to our study or not. Assuming this interpretation is correct, a derived and analytic expression for the S factor fitted to experimental data across a broad range of systems. However, complete physical explanation for the hindrance effect remains elusive, adding a repulsive contribution to the union potential enables the reproduction of the observed behavior. This repulsive term has been suggested to arise at least partially from a proper treatment of the Pauli repulsion. Motivated by experimental constraints, we adopted the more elastic hindrance plus resonance model proposed by the M22 for the case of the carbon 12 plus carbon 12 to describe the hindrance scenario for the carbon 12 plus oxygen 16 and oxygen 16 plus oxygen 16 systems. We used the phenomenological formulation of the S factor maximum provided by the Jiang and his colleagues in 2007. Starting from these expressions, so for the total factor, we derive the corresponding non-resonant nuclear reaction rates for each channel. I mean that proton, alpha, and neutron. The branching ratio for each channel are assumed to follow those of C58 except for 12, carbon 12 plus carbon 12 where experimentally derived branching ratios of 65 up to 35% are adopted in favor of the alpha exit channel. We refer to this approach as the hindrance risk scenario, which differs from the full hindrance model as explored in M22 and T24 by including the resonance only for the carbon 12 plus carbon 12 reaction given the lack of the clear experimental resonance data within the gamma window for carbon 12 plus oxygen 16 and oxygen 16 plus oxygen 16. Figure 1 shows the relative deviations from the CFH of the rates obtained under the hindrance race scenario as a function of temperature. The carbon negative and oxygen burning temperature regimes are given for the 15 and 17 M star models. For these masses, we expect the hindrance to impact the carbon 12 plus oxygen 16 reaction, while its influence on the oxygen 16 plus oxygen 16 reaction is expected to be minor since suppression in the cross-section predominantly occurs at temperatures below these relevant for core oxygen burning. Now I want to go through the time-dependent Hartree Folk framework as a complementary approach to the previous data-driven models. We choose to explore a test scenario, the impact of nuclear reactions rates derived from the fully microscopic TDHF mean field theory. For a detailed description of this method, see example. Similar 2025 TDHF simulations describe the time evolution of the occupied nuclear wave function in the self-consistent mean field generated by the ensemble of nucleons. The many body state is constrained to be an anti-symmetrized product of single particle states. For example, Slater determinant at all times. The main input is the energy density functions EDF with the characteristics to effective nuclear-nuclear interactions. Although most applications are based on the Skyrim EDFF or energy density function. Recent calculations with the finite energy orange Gaussian interaction and including pairing correlations have also been performed by Scam and Hashimoto in 2019. A significant advantage of the TDHF approach is that it describes both nuclear structure and dynamics on the same footing. In particular, EDF or energy density functional parameters are only fitted to the nuclear structure's data and equation of state properties without relying on input from nuclear reactions. Modern TDHF calculations can now be performed in full three dimensions without imposing constraints on the system's shape evolution. The weakness of the real-time mean field method is that it cannot account for the quantum tunneling expected in the sub-barrier fusion. To overcome these predictions are obtained by calculating the nuclear synchronous potential at an energy just above the Colombo barrier using the so-called density constraint CDHF method. TDHF. The resulting potential is then used to compute barrier transmission probabilities at the sub-barrier energies through one-barrier penetration methods. Importantly, DCTDHF potentials account for crucial dynamic effects such as nucleus transfer, which may significantly impact sub-barrier fusion cross-sections. DCTDHF calculations were performed in Godboy and his colleagues in 2019 for the case of carbon-12 plus carbon-12 system, which is also considered in the present work here. Calculations based on the CLY4D in 1994 by Kim and his colleagues on UNEDFR and QMC EDFS are used. The trend obtained are very similar for these three models and show an increase of this factor at low energies. In contrast to the inverse scenario, see applications B1. Tau is still several order of magnitude lower than the predictions from the THM discussed above. For our sensitivity study, we choose to adopt the predictions obtained with the primary SLY for the functional. For the two other systems, carbon-12 plus oxygen 16 and oxygen 16 plus oxygen 16, we perform analogous calculations using the same methodology as in Godboy and his colleagues in 2019. The resulting nuclear rates are shown in Figure 1 and compared to the CF88 and hindrance rates at the temperatures where core and shows carbon negative and oxygen burning are predicted to occur. The TDHF rates are slightly higher than those of CF88 by less than 1 dex. In contrast, the hindrance scenario yields significantly lower rates up to two orders of magnitude at these temperatures, suggesting it may lead to the largest differences in the results. Neutron source nuclear reactions as the main contributor to free neutrons during massive star evolution, the rate of the neutron 22 alpha and 25 magnesium reaction has also been updated according to Oxley and Scully's 2021. This reaction is in a competition with the Na22 alpha gamma 26 magnesium, whose rate has also been updated based on the same reference. These updated rates differ significantly from previous evolutions, and their reliability is still under debate, with additional experimental measurements expected to clarify the situation. For this study, we adopt these new rates to obtain a fair estimation of its impact on massive star nucleosynthesis. Rates from the AXOI 2021 are approximately twice as high as those from the Langland and skeleton 2012 and are expected to enhance the free neutron density during the carbon to oxygen burning phases. The second main contributor to free neutrons comes from the carbon 13 alpha and oxygen 6 reaction. In D24, we use the rates from the NOCRI compilation by the aid of the Anglo and his colleagues, that was written in the 1991 99 But we now adopt to update rates proposed Sinai and Scarlett in 2021. This new reference results in the reduced neutron production while preserving a high carbon 13 abundance throughout the helium burning phase. There is broad consensus regarding the reliability of this neutron source reaction rates from the original NetGen database, and in line with recent references, we have updated four additional linked reactions as listed in tab 2. Finally, we note that the update of the carbon 12 alpha gamma oxygen 6 reaction should not alter significantly that the S process nuclear synthesis as demonstrated by the De Boer and Scarlett in 2017. Now I want to go to the nuclear reaction rates impact from the carbon burning to oxygen burning. General evolution, part 4.1. In this section, we compare the evolutionary outcomes of the rotating models under each of the three nuclear reaction rate scenarios: CF88, hindrance rates, and DDHF, described in detail in section 3. Figure 2 shows the revolution of the central temperature and density of R15 models. For each of the three nuclear reactions, rates references a model from the D24 are also included in the figure for comparison. Compared to the D24 models computed up to an ignition. The new models exhibit a hotter and denser core. There is a consequence of the updated reaction rates for carbon 12, alpha gamma oxygen 16 during the helium burning phase and the revision of the equation of states in the advanced phases. As observed in the 224 and carbon ignition, conditions depend on the reaction rates, and the new models ignition occurs at the lower temperatures in TDHF and at higher temperatures in hindrance rays relative to the CF88 model. We note that the overall shift to higher temperatures in the new models compared to D24 reduces the difference between the whereas as the carbon burning temperature of the 15M star are now closer to the peak of the resonance, where the CF88 and hindrance rays converge. See the top right panel in figure 1. Similar behavior can be observed for oxygen ignition, where the two models following the hindrance scenario show a shift towards ignition in a denser and hotter core. Changes in the rates can also be observed from the perspective of the energy output associated with the various reactions during the evolution. In figure 3, we show the total energy production profile for rotating 15M star during the shell carbon burning and core oxygen burning phases. For each of the nuclear rate prescriptions explored in this slide, nuclear energy produced in the core or in the shell is compared to the neutron energy loss, which becomes significant during the core carbon burning phase. A moderate difference between models are observed, mainly reflecting the readjustment of the solar structure, which compensates the lower hindrance rates by higher central temperature and shorter burning lifetime, resulting in a model's increase in central energy production. You see, figure 3 illustrates the energy production rates belongs to the ERG per GS inside at 15M rotating star for varying reaction rates. Left sections energy during the carbon burning approximately 2000 years after core carbon ignition. Right sections energy during the core oxygen burning and central oxygen oxygen 16 is equal to 0.3. The pale areas in orange indicate where the gravitational energy is negative, for example, corresponding to an expansion. Table 3 describes core burning lifetimes in years for rotating and non-rotating stars of 15, 17, and 20M as a function of the adopted nuclear reaction rates. Now I want to go through the next sections, which is burning lifetime. The durations of the various nuclear burning phases are especially sensitive to change in the reaction rates. We observe significant differences in the present world compared to the values reported in D24, which we attribute to the updated reference for the carbon 12 alpha gamma oxygen 16 reaction. As discussed in section 3.1, the rates from the Deborah and his colleagues 2017 increased the ratio of the carbon 12 per oxygen 16 from about 0.45 to about 0.51 in the case of 15M model, as can be seen in the figure 4. In parallel with this increase, the change in carbon 12 alpha gamma oxygen 16 rates also leads to a reduction in the amount of the Ne20 produced as helium exhaustion. This helium exhaustion overall the transition from the Coons and his colleagues in 2002 rate results in shorter helium, nickel, and oxygen burning lifetimes and an extended carbon burning phase. Regarding the impact of fusion reaction rates variations under the three scenarios, Tapter presents the lifetimes for the carbon burning, burning, and oxygen burning phases for rotating and non-rotating models across the explored mass range to determine these lifetimes. We define the ignition point as the moment when the central mass fractions of the main fuel element decreases by 3 multiplied 10 to the power of minus 3 from its maximum value, its fuel maximum. We define the point of the exhaustion as the time when the central mass fraction reaches the maximum, its fuel minimum set to the 10 to the power of minus 5 for carbon and 10 to the power of minus 3 for nickel and oxygen. In other words, the phase lifetime is T its fuel maximum minus 3 multiplied by 10 to the power of minus 3 Tx fuel minimum at the lower rates from the hindrance result in comparable or slightly shorter carbon burning lifetimes with a numerical uncertainty of about 100 years. In contrast, the higher reaction rates from the TDHF model led to a significant increase in carbon burning lifetime for all models relative to the CF88 reference. This result may appear counterintuitive, as one might expect lower rates to yield longer lifetimes due to the less efficient burning. However, as observed by M22 and D24, reduced diffusion probabilities decreases the energy output in the burning core. To maintain hydrostatic equilibrium, the star then responds by contracting its core, which in turn heats up see the process in figure 2, thus boosting the burning and reducing the phase lifetime. Additionally, the lower fusion probability delays ignition to higher densities, further shortening lifetime. For any burning phase, differences between the models are less significant, and a no clear monotonic trend emerges in the resonant responses to the change in carbon 12 plus carbon 12 reaction rates, as previously noted by Bent and colleagues 2012. Indeed, for the advanced Na and oxygen burning phase, the lifetime is governed by a more complex interplay between the central temperature reached at the end of the carbon burning and residual abundance of Na and oxygen. The oxygen burning lifetime are notably shorter in the hindrance model due to both a lower amount of available oxygen 16 and the corresponding reduced oxygen 16 plus oxygen 16 reaction rates. This result reflects the same underlying mechanism discussed for the carbon 12 plus carbon 12 reaction, with ignition conditions shifted to the higher temperatures and densities As shown in Figure 2, as suggested by Figure 1, the C58 anti-DHF models yield similar oxygen burning a lifetime due to their nearly identical rates at oxygen burning temperatures. Finally, we note that both rotating and non-rotating models exhibit trends consistent with those reported into D24. We refer the reader there for further details. Now I want to go through the stellar structure, the chemical structure of the most abundant elements is shown in Figure 5. At the end of the carbon bending and oxygen bending phases for the 15M star and each of the nuclear reaction or rate scenario considered. At the end of the carbon bending phase, all models predict similar to monoxide carbon core sizes of about 2.50 m. In the center, chemical abundances are impacted by the change in reaction rates. The most striking difference is observed for natrium-23, whose abundance is three times higher in the TDHF model. In the other two scenarios, this enhancement is attributed to a lower efficiency in the conversions of natrium-23 into natrium into Ne20 via subsequent P alpha reactions due to the lower central temperature. The extent of the carbon shells is also significantly impacted by the choice reactions rates as already noted in M22 in application D1. We show the Kippenhahn diagrams for the 20M model under each scenario. It is clear that the highest rates from the TDHF produce the least extended convective carbon burning shell, while the lowest rates from the hindrance results in more extended shell. The right panel of Figure 5 shows abundance profiles. At the end of the oxygen burning phase, silicon 28 and sulfur 32 and sulfur 34 isotope are the main products of this phase, formed through secondary reactions involving the primary silicon 28 and phosphor 31 products mentioned in equation 3, leading notably to a larger abundance of sulfur 34, consistent with the finding by Farmer and his colleagues in 2016. This amount of sulfur 34 is lower in the CF88 model compared to the 2DHF and hindrance cases. Moreover, the lower hindrance rates result in the reduced central abundance of silicon 38 relative to a CF88 and TDHF. The resulting silicon core mass MSI is smaller for the CF88 and TDHF model is about 1.10 than for hindrance 1.20 m, defined by its silicon and its sulfur is less than 0.2. In agreement with the results in the Hinrishi and his colleagues 2004, at the end of the oxygen burning, other elements are also affected, such as the titanium 44, which is especially less abundant in the TDHF model compared to the other two scenarios, with mass fraction reaching only 6 multiplied by 10 to the power of minus 9 instead of 4 up to 7 multiplied by 10 to the power to the 10 to the power minus 8 in the CF88 and hindrance models. To sum up, carbon 12 plus carbon 12, oxygen 16, and oxygen 16 rate variations impact the chemical structure and central abundances of several elements and the silicon core mass at the end of the oxygen burning phase. However, they have a negligible influence on the size of the carbon monoxide core at the evolutionary phase. Now I want to go to the nucleosynthesis. Neutron capture processes are believed to be at the origin of the most heavy elements in the universe. You can see the Acrons in 2023. One of these, the slow neutron capture process, S process, develops in the massive stars at neutron densities of the order of a neutron n is equal to 10 to the power of 5 minus 10 to the power of 10 1 per cubic centimeter. It occurs mainly during the core helium burning phase, for example, Langer and his colleagues reach neutron Ne22 alpha and 25 magnesium at the main neutron source. The carbon 13 alpha and oxygen 16 reaction produces a short neutron bursts at the onset of the core helium burning, barely producing heavy elements. These S-process elements are subsequently transported to the outer stellar layers over the relatively long duration of the helium burning phase. During the brief advanced evolutionary stage, the carbon burning shell also contributes to the S-process. Minor contributions are also expected during the core carbon burning phase. In this specific phase, rapid transport of nucleosynthesis products from the core to the outer shells should be involved to enable this process to contribute to the chemical galactic enrichment. During the core oxygen burning phase, trans ion elements are destroyed via photo-disintegration reactions. In addition, rotation is now to boost this process during core helium burning by the promotion, the synthesis of the primary carbon 13 and Ne22. The impact of the variations in nuclear reactions rates and rotation parameters manifest mainly to changes in center temperatures throughout solar evolution and modifications in burning lifetime, both of which influence the neutron exposure. Indeed, the two main neutron sources for S process in massive stars, carbon 13 and nickel 22, and contribute in different proportion depending on the temperature and evolutionary stage. In this context, we have also updated the seven important reactions for S process nucleosynthesis as listed in T tab 2 and introduced in section 3. Now I want to go through the next section, one Joule code for nucleosynthesis. We explored the implications for nucleosynthesis using the one Joule code described in Choplin and his colleagues in 2016 and previously applied in other works. M22 and D24. The nuclear network has been extended to track 1,454 isotopes against 737 in the previous versions indeed to T4 in order to capture photo disintegration reactions during the core oxygen burning phase. In this approach, only a single thermodynamic trajectory in temperature and density is followed. Either core or shell and transport procedures such as convection are neglected. This simplified method provides reliable predictions for the S-process nucleosynthesis during the core helium burning phase. For example, for Frost Shane and his colleagues in 2022. During these advanced evolutionary phases, rotational transport is still active but exerts a weaker mixing influence due to the short time scales in late stellar evolution, as shown, for example, in Figure 2 by Chaplin and scholars in 2017. Thus, this approach is sufficient to capture and interpret the relative effects introduced by variations in nuclear reaction rates. Numerous studies have investigated S-process nucleosynthesis in the core and shell regions during the advanced phase of evolution. Now I'm going to go through the S-process nucleosynthesis. We now explore the isotope abundance predictions obtained from the one-gene code at the end of the core oxygen burning and shell carbon burning in our 15M rotating models, where the slightly lower temperatures reach the are expected to enhance the sensitivity to differences among the nuclear reaction rates prescriptions. See Figure 1 or D24. We first examine the chemical evolution of the core following the same approach as in M22 and D24 by tracking the central density and temperature throughout the successive core carbon and Ne oxygen burning phases. Figure 6 shows The production of the boost-direct carbon-bearing products such as Ne and natrium and magnesium and transition elements during the core carbon burning phase. After Ne burning, then subsequent oxygen burning phase will lead to the destruction of most iron elements and the synthesis of the typical oxygen burning products including silicon, sulfur, argon, calcium, and titanium are as also observed in the right panel of figure 5 at the end of the Kirk's burning phase, heavy elements exhibit either lower Z is greater than 30 and less than 30 or almost null when the Z is greater than 40 elements as colored line in figure 6. This is due to photon dissociation reactions such as gamma and gamma P and gamma alpha, which becomes increasingly efficient at the temperatures greater than 1.8 Kelvin, typically reached during the oxygen burning phase. The South structure reflects odd even effects in the nuclear bending energies due to the pairing and is clearly visible in the abundance pattern at the end of the oxygen barreling below. Beyond the low abundance of fluorine, Z is equal to 9, the largest deviations up to 1 dex relative to the CF88 reference are obtained for the hindrance. These features a modus over production of the light element between calcium Z is equal to 20 and Fermi Z is equal to 26 and under production of S process elements at Z is greater than 30, such as GE, SE, or SR, we mainly observe consequences of the lower rates associated with the hindrance scenario for oxygen 16 and oxygen 16 reaction, which leads to the shorter burning phase and reduced neutron exposure. This mirrors the behavior seen into D24 for the carbon 12 plus carbon 12 reaction during core carbon burning phase. It is worth noting that the cutoff for Z is greater than 40 is unaffected by the choice of the reaction rates. In all models, the S process distribution in the core is further modifying during the carbon burning shell episodes. Thank you so much for watching my tutorial video until the end. If there is any simulation for this literature that I read it for you, you can find it from my github.com slash maxo script, github.com slash kashi script, or github.com slash sephora script. Today is the end day of the June 2026. Time is almost the midnight.